Hello and welcome to our presentation. We are a computer science capstone team from Portland State University, where we built a proof of concept EPCIS supply chain distributed ledger. So what does that exactly mean? Well, in any supply chain, it is important for businesses to effectively communicate information with each other. To that end, GS1 has created the global standard for business events, EPCIS, or to give it its full title, Electronic Product Code Information Services. However, how can businesses, or consumers for that matter, have faith they know a product's true origin or if it has met regulatory requirements? This is why we leverage the IOTA Tangle, an immutable, open source distributed ledger where once data is uploaded, it cannot be tampered with. So the goal for our project was to see if we could utilize these two pieces of technology to create a tool for a more transparent and efficient supply chain. Our sponsor was John McConnell from Dailogic, and our team consisted of myself, Gilbert Grundy, as team lead, Joshua Meng, Dan Scott, Joel Williams, Margarita Maligaya, Jaylen Figueroa, and Matthew Berzinskas. First off, we are going to have demos of our Android and web app, and later we will detail our tech stack.
Hi, I'm Matthew, and I'm going to be discussing our fictional company, Schrodinger Motors. For purposes of this project, we thought it would be compelling to follow a product that exists in the sustainability space, while also posing its own environmental and sourcing problems. Towards that goal, we chose the journey of an electric car battery. From manufacture to vehicle sale, this diagram demonstrates a series of steps in the supply chain and relevant EPCIS events that would be captured and managed by our software. Using scanner data, we are able to convert the activity to standardized EPCIS format and upload it to a distributed ledger, making it immutable. A consumer or business would be able to query and retrieve this information and be confident in its validity. Next, I will demonstrate the mobile application handling two of these cases. Here we see the default launch screen, which requires configuring the device before use. This is done via scanning a QR code to some pre-configured JSON. After scanning a transaction event config file, a confirmation message comes up and we enter the transaction scanner. First, we can scan an EPC, and then we can scan some associated business document. Here we'll scan a link to a test procedure. After scanning the QR code, the app will detect it's a PDF and ask if you want to generate a checksum. On submitting, we see a full EPCIS JSON of the event and the included checksum. Exiting out, we can reconfigure the device for a separate event. This time we'll pull up an aggregation event. First, we can scan a shipping label and then associated products in succession. Here we capture 4 EPCs using a quick capture method. At the end, we can submit, view JSON, and post to our API as before. And that concludes this demonstration.
Hi, my name is Josh, and I'm going to walk us through a demo of our web app. This app was made so that the batteries from Schrodinger Motors can be tracked as they move along the supply chain. Our app is built with Django. It interfaces with our REST API to expose EPCIS events to users. We are currently looking at the homepage. From here, we can access search portals, the complete history of the batteries, a list of all product codes, and an about page. First, we'll check out the list of all product codes. These are all the electronic product codes currently on the Tangle. Now we will search for an EPC via the serialized global trade item number search. This sends a call to our API, which then grabs the event from the Tangle and returns it to the web app. Here we can view the data about the event. Note the PDF within the biz transaction list. The Android app included a URL to the PDF and generated a MD5 hash of the PDF when the event was first created. It's important that we ensure that the PDF has not been altered in any way. When the web app loads the event, a MD5 hash is generated of the provided PDF in its current state. The two hash values are then compared, and the PDF will either pass or fail verification. This is important because it gives validity to the included document. Next, let's take a look at the entire battery history. Here we can select from any of the 4 categories to get more information. Finally, we will check out the About page. It gives a brief description of our project. Global supply chains are broader and more complex than ever before. Many products have international supply chains involving multiple industries with varying regulatory needs and nuances. Companies will have different levels of relationships and may have limited confidence and/or difficulty interpreting shared business data. The benefit of having a global standard such as EPCIS 2.0 is to give businesses a common language to communicate business events to each other. Additionally, the IOTA Tangle provides an immutable ledger that can instill trust in data exchanged between disparate businesses with little regulatory oversight. The target audience for a secure supply chain is immense.
Hey everyone, this is Jaylen, and here are the main features. Some of the main features of our full stack application include a REST API, a mobile scanner app, and a web app. Our mobile scanning app captures and pushes events to our API. The web application retrieves from our API and displays event information to the end user. Both mobile and web applications utilize our REST API to connect to the IOTA Tangle and fetch EPCIS events from the IOTA Tangle. As far as our REST API goes, it uses IOTA's Node.js client library for Tangle interactions, provides multiple endpoints for EPCIS fields in which we implemented. It uses cursor pagination for EPCIS doc GET requests, CI/CD pipeline with unit tests and integration tests, and Postgres SQL for our database in which we use message indexes and message IDs to retrieve EPCIS events from the IOTA Tangle. Some of the limitations include infrastructure, which is minimally sufficient for a small set of EPCIS events, which basically means that our code is not production ready and requires more planning for scalability. It could also be further optimized for speedy querying and concurrency, which it is currently not in its current state. Future improvements include auto-scaling with the API with Kubernetes and Docker containers. As far as our mobile scanner app goes, it was written in Java ZML through Android Studio. It's configurable to record specific EPCIS events, which include object events, transformation events, transaction events, and much more. It creates EPCIS events in a GS1 approved format and posts to the API. It also has limited ability to capture and checksum PDF documents. Some limitations include it's only limited to scanning GS1 data matrix barcodes. It also requires configuration files for scanning, and it does not include all EPCIS fields in which EPCIS 2.0 uses. Future improvements include more robust barcode validation.
I'm Margarita, and I will be discussing the web application of our project. Our web app was created using Python's Django framework, HTML, and CSS. This front-end portion allows users, whether consumers or businesses, to manually search for the EPCIS events of a specific electronic product code or look through the database. They can also look for events tied with a specific business step, such as shipping, inspecting, and more. There's also a verification aspect that verifies whether a PDF file in the event is in its original form, which reassures the user that no data has been tampered with. The web app was designed to be user-friendly, converting tons of JSON data into something easy to read and navigate. There is room for improvement, such as parsing the JSON from the API more efficiently, using backend processes to help the web app run faster, and to move to a different framework that doesn't focus on databases.
Hi, I'm Joel Williams, and today I'll be giving an overview of our project's high-level architecture and tech stack, as our project is made up of several components which interact together to provide the service as a whole. As Matthew showed us, a front-end user interacts with our service by first having a product with a barcode where some business event occurs, something like an observe event or an aggregation event. The journey of our event through our service starts with the Android app, which provides the scanning functionality. From that scan, the mobile app generates the EPCIS event specified by the user and stores that event into a JSON document. The mobile app then sends that document to our REST API endpoint, where the event is validated according to EPCIS specifications for correctness. If the validation is passed, the API loads the EPCIS event ID and any associated sub-IDs into the API's query database. The query database only stores hash IDs to query the tangle, and does not store any other information about the EPCIS event other than the minimal data needed to provide the EPCIS specified API endpoints. Once the event IDs are loaded into the query database, the API uploads the event and its full JSON contents to the IOTA tangle for storage. Dan will provide a more in-depth overview of what the IOTA tangle is later in the presentation, but very briefly, the IOTA tangle is our event database on a distributed ledger where our events are supposedly immutable and verified by other nodes on the tangle. Suppose a supplier has a barcode or location code that they want to look up and see all the events that have happened for that code. Using our web application, the supplier would enter in the query, the application calls out to our API, which queries our ID database, and then fetches that ID or IDs from the tangle, then returns that data to the user with the full information associated with that event from the tangle. Our project has a lot of moving parts and a stack of technologies is needed to make this all work. At the top, we have the IOTA tangle where our EPCIS events are stored. The tangle is distributed and unmanaged by us, therefore it is above our infrastructure layer on the stack. To provide the infrastructure for our project, we use two AWS EC2 instances to run our API and querying database. Our GitLab repository, which hosts our API code, uses a CI/CD pipeline to deploy directly to the AWS node. The pipeline has stages for linting, unit testing, and database integration testing via a Postgres Docker container. Our web application is deployed to the Heroku cloud. We used 4 languages in various components of our project. The mobile application was written in Java with some sprinklings of Kotlin. The API was written in Node.js, and our application was written in the Django framework in Python. Finally, an EPCIS document is our data layer, which is a format specified by GS1, an organization dedicated to providing business standard language all over the world. These documents are stored in JSON format, and EPCIS 2.0 allows JSON LD format, which provides the capability to encode links in JSON.
The IOTA tangle is a distributed ledger technology that utilizes directed acyclic graphs. The network is composed of nodes that issue transactions from users and work to approve other transactions. This proof of work is a cryptographic puzzle similar to blockchain technologies. The benefits we gain by utilizing the tangle are immutable data storage and broad access to that data once stored on the tangle. A desired feature for this project was uploading supply chain related documents, such as material safety data sheets, but the tangle in its current form has a max payload size of 32 kilobytes, which limits our ability to attach documents to messages. As a workaround, our Android application creates an MD5 hash from a web-hosted PDF and stores both the hash value and a URL to the PDF in EPCIS event data. When our web application tries to retrieve the EPCIS event, it pulls the PDF from the URL, creates another MD5 hash, and compares the 2 hashes to verify the PDF's validity. Conflicting events can also exist on the tangle simultaneously, but will be resolved through a comparison of transaction weights when encountered. Our schedule began with weekly and bi-weekly meetings from October through December for research and development, and transitioned into 2-week sprints from January to March for project implementation. Our main points of focus during research and development were IOTA and EPCIS 2.0 technologies. Implementation began with our Android application and REST API on January 3rd, and a minimum viable product was reached at the beginning of our 4th sprint. Development and refinement will continue throughout the winter term, which ends in mid-March.
The project was divided into 3 main teams. Gilbert, Dan, Joel, and Jaylen worked on the REST API, Josh and I worked on developing the web application, and Matthew worked on the mobile Android app. Though members self-assigned tasks and roles from the beginning, everyone was flexible and willing to help each other out based on the needs of the project. Members were extremely efficient and productive, however, we'd like to give a special recognition to a few. Matthew worked on the mobile Android application single-handedly with minimal help from others. Gilbert was a great team lead who was flexible in helping different parts of the project, as well as organizing tasks and meetings. And Joel, who set up the pipeline, AWS instances, and Docker components. Now that we've concluded our Capstone project, we can all say that we've learned a lot, like how to collaborate with a bigger team, the process of developing a full-stack product, how to resolve different opinions within the group, and how to work with languages and technologies we may not all be familiar with. We also wanted to share some advice for future Capstone teams. Aim to get your minimum viable product as soon as possible, then you can iterate on it. Team building activities are fun and can help your team bond and be more comfortable with each other. Use a workflow process that works best for your team, and lastly, be flexible and understanding during the entire process and help your team members out.
Some unexpected events include shortcomings of decentralization with IOTA. In our research with IOTA, we came to the conclusion that it's not fully decentralized in its current state. This is because it uses coordinator nodes, which determine which transactions are available to attach to the network and which ones are not. As far as DevNet message removal goes, we encountered some issues where some of the EPCIS events that we pushed up to the IOTA tangle were removed. We also experienced Heroku timeouts due to Changle retrieve time. This was the issue on our API end, in which we had to rewrite some of our code base. Finalization of EPCIS 2.0 is still underway, and it is still currently changing as we are recording this presentation. Also, our API node decided to stop working on the day of presentation, so we dedicated a few hours to get it up and running in time for our presentation.
Hi, Gilbert here again to discuss a few potential areas of future development. For a production rate application, there would need to be some time spent developing user profiles with security credentials to ensure the integrity of data being uploaded to the tangle. Otherwise, a bad actor could upload fake events and create a false history for a product. Additionally, the Android app as is not very feature rich. It sends a specific set of EPCIS events, but this can be made to be configurable so the end user could have the ability to create custom EPCIS events. EPCIS 2.0 also specifies a queries endpoint, which we didn't implement for our project because it accepts arguments in the EPCIS query language. And for this to be compatible with IOTA, we have needed to have created a far more involved data storage system. Because all data within the EPCIS events would be queryable, we would have needed to mirror all the data held in individual EPCIS events off the tangle so they could be successfully queried on the tangle. Finally, IOTA has Solidity smart contracts in beta, providing the possibility of consumer-to-consumer smart contracts in the future, which could be leveraged to give added value to products by giving customers the ability to record aftermarket transactions on the EPCIS ledger. Here you can access our Heroku web app endpoint and our project code on GitLab. Here is some feedback that our sponsor John wrote. Talking with him, I believe he was very happy with our progress throughout the 2 terms. As he states, a production level application would be more user role based. He's expressed to us that he's very much looking forward to our final report, which we are currently writing and we'll be handing in next week. Finally, I just want to say thank you for watching. Thank you, John, for all your help. We couldn't have asked for a better sponsor. I also want to say thank you to the entire team. It was a pleasure working on this project. It was a really interesting project, and I think we got a lot of great work done by having some fun. Thank you.